Hi, welcome back. Last time we introduced the idea of an electron configuration and an orbital diagram and looked at examples for the first four elements in the periodic table. And we're going to continue um, looking at the elements and get into some more complicated examples. We're going to turn our attention next to boron, which is up here next to carbon in the periodic table. Boron has all the same electrons that beryllium had. Beryllium had its electrons in the 1s orbital and the 2s orbital. And the next place where electrons can go is into the 2p sublevel. And so boron will put its fifth electron into the 2p sublevel. It has a configuration with a helium core and then 2s2, 2p1. So the 2s2, 2p1 are the valence electrons in a boron atom. And we can represent those valence electrons with an orbital diagram like this. We have a pair of electrons in the 2s orbital and then a single electron in the 2p. So moving along to carbon, the carbon sort of continues the story. The next electron that pops in is going to also go into the 2p sublevel. So the configuration for carbon will be helium core, 2s2, 2p2. And now when we come to write the orbital diagram, the 2s2 electrons will be paired up in the 2s orbital, but there are a few choices that we have for where the electrons can go in the 2p sublevel, and that's because there are three orbitals in that sublevel. We can put the first electron into any one of the three. That doesn't really matter. But the second one, we actually have three choices. We could pair up the next electron with the first one in one of those p orbitals. We could put the second electron into a different p orbital with an opposite spin, or we could put the next electron into a different p orbital with the same spin as the previous one. And of these options, the one on top is the worst because having two electrons in the same orbital creates the most repulsive forces. And of the other two options, for complicated reasons, it turns out that the lower option has the least energy, and so that is what the electrons end up doing. They end up moving into separate orbitals with their spins parallel, going in the same direction, and so that's the situation that we've got in a carbon atom. And then moving along to nitrogen, nitrogen adds one more electron. That's going to go into the 2p sublevel, and it will go into the third of those p orbitals with its spin in the same direction as the first two. And then moving along to oxygen, oxygen will add one more electron in the p sublevel, and this electron has no choice but to pair up in one of those p orbitals, and so it does so. This is what the valence shell of oxygen looks like. Fluorine will add its next electron into the p sublevel as well. And then finally, neon will put a sixth electron into the p sublevel. Its electron configuration is helium core, 2s2, 2p6, and its orbital diagram has all of the second level filled in. And so neon fills up the second energy level that's available in an atom. So moving along then, the next element is sodium. And sodium, there's no room in the first or second energy levels for the next electron, and so sodium is going to have to put an electron into the third energy level. And so for sodium, the core now looks like neon, and the valence shell is the third energy level. And so the next electron is going to go into the 3s sublevel. Sodium has a configuration with a neon core and then 3s1, and its orbital diagram has an electron in the 3s. Magnesium will put another electron into the 3s. No surprises there. And then aluminum is going to put its next electron into the 3p sublevel. And so it has a configuration of neon core 3s2 3p1. And then the rest, the next 5 elements will put their valence electrons. They will be filling in the p sublevel, so that by the time you get to argon, the configuration is neon core 3s2 3p6. And so you may be so argon closes off the 3rd energy level, so let's go ahead and put that in. So you may be starting to see why the periodic table is organized the way it is, why it has this funny looking shape. Atoms that are in a particular group have valence electron configurations that are similar. So sodium has its valence electron in the 3s orbital. The element above it, lithium, had its valence electron in the 2s orbital. Hydrogen had its valence electron in the 1s orbital. Similarly, boron had a valence electron configuration of 2s2 2p1. Aluminum, which is right under boron, has an electron configuration of 3s2 3p1 for its valence electrons. And likewise, the noble gases, helium, neon, argon, all have the common feature that they have their valence electron shell all filled up with electrons. And we can continue looking at larger atoms. So moving further, potassium will have a core that looks like the argon atom, and its valence shell will be the 4th energy level. And so it will have it will add an electron into the 4s orbital, getting a configuration of argon core 4s1. And so it has a valence orbital diagram with an electron in the 4s orbital. Calcium adds a 2nd electron to the 4s orbital. And then scandium, the next element, it's the next available orbital to put the electron in is in the 3d sublevel over here. And so the outermost electron in scandium is going to go into the 3d sublevel. It has an electron configuration of argon 4s2 3d1. And it has an orbital diagram for the valence electrons that looks like this. And then the next 9 elements, titanium through zinc, just add their electrons into the 3d sublevel and fill it in. And then when we get to the next element, gallium, will put an electron into the next sublevel, which is 4p. It has a configuration of argon 4s2 3d10 4p1. This is its orbital diagram. And then the next 5 elements, germanium, arsenic, selenium, bromine, and krypton, will just go into filling in the 4p sublevel. So that krypton has a configuration of argon 4s2 3d10 4p6. And so krypton fills in the 4th energy level that's available to the atom. And then we can continue. After krypton come rubidium and strontium. There they put electrons into the 5s sublevel. And then the next 10 elements put electrons into the 4d sublevel. And then then the next is we fill in the 5p sublevel. Xenon closes off energy level 5. And then cesium and barium put electrons into 6s. After 6s, the periodic table sort of takes a little detour, and the next sublevel to fill in is actually 4f. And so you get 14 electrons going into the 4f sublevel, followed by the 5d, and then the 6p. At that point, we get to radon, which closes off the 6th energy level. And then francium and radium put electrons into 7s. Next, we put electrons into the 5f sublevel, and then the 6d, and then the 7p, and finally organoson closes off the 7th energy level. And so the different parts of the periodic table involve valence electrons in the different sublevels. And so the alkaline metals and the alkaline earth metals all belong to the s block of the periodic table. Their outermost electrons are in an s orbital, and then the other main group elements are located in the p block. They have their outermost electrons are in a p sublevel. The transition metals form the d block. Their outermost electrons are in a d sublevel. And then your inner transition metals are in the f block. Their outermost electrons are in an f sublevel. And so if you understand this relationship between the building up principle of electron configurations and the structure of the periodic table, you can start to write electron configurations just using the periodic table itself. And so let's look at a couple examples of how you would do that. So the first example I'm going to choose is antimony, symbol SB. And if we wanted to write down the electron configuration for antimony, we first notice that it is in the 5th row of the periodic table, the 5th period, and it follows, and it's going to have a core that corresponds to krypton. So krypton is going to be the core, and then we've got the 5s sublevel is going to be filled in, and then the d electrons next to that are going to be 4d. So we've got 10 of those 4d electrons, and then 3 more electrons will go into the 5p sublevel. So the electron configuration is krypton, 5s2, 4d10, 5p3. This is its orbital diagram. And then the other example I wanted to look at is tungsten. Tungsten has the chemical symbol W, and it is in the 6th period of the periodic table. It's going to have a xenon core, followed by 6s2, and then we need to remember that there's a detour. After barium comes lanthanum, and so after the 6s, we fill in the 4f sublevel, and there are 14 electrons there, and then finally we put 4 electrons into the 5d sublevel. And so tungsten has an electron configuration of xenon, 6s2, 4f14, 5d4, and this is its orbital diagram. And this will be a good place for us to finish this video.